Okay, so in order to determine the amount of moles at equilibrium, of course we have to use the concentration that's at equilibrium. So for part B, let's take a look here. So for part B, if the concentration of HI at equilibrium that we solved for in the last section, so part A, was 3.12 moles per liter. Okay, so keep in mind, don't use the rounded answer. You want to use like not the 3.1. You want to use the full concentration when you're doing this because you're continuing the calculations, right? So we have the moles per liter, and remember we had the volume of the container. So that was given at the very beginning of the question. We have a 0.5 liter container. So essentially what you're doing is you're just rearranging this formula to solve for the moles. So you have the equilibrium concentration, you have the volume. We can solve for the moles at equilibrium, which is essentially C times V, right? So the mole value here would be 3.12 moles per liter times 0.5 liters, which of course give us units of moles. So we have 1.56 moles, okay? For part C, you're pretty much doing exactly the same thing, because the amount of of hydrogen and iodine that are left unreacted is essentially the same thing as saying at equilibrium, right? So they're saying once the reaction seems to be completed, which we know really it's in equilibrium, so it's continuously going back and forth, but they want to know how much reactant is remaining. So the concentration of hydrogen, and actually iodine is going to be the same thing at equilibrium, we found to be 0.44 moles per liter. So you're essentially doing the exact same thing that we did up here, except you're doing it for the reactants, right? So the value of moles is going to be C times V, so it's going to be 0.44 moles per liter times 0.5 liters, which will give us a value of 0.22 moles of each, right? So there's 0.22 moles of hydrogen, 0.22 moles of iodine that are left unreacted at equilibrium. Okay, so we're going to use these two values in a later question, so you'll see what I mean in a second here. Okay, so part D says, if the conversion of H and I to HI were essentially complete, what amount of HI would be present? Okay, so what they're asking for here is, if we were to assume that this were to go to completion, so meaning we had all product that's produced, right? Like 100% of this became product, what amount of HI would be done? So what they're basically asking here is they're asking you to use stoichiometry to determine what the value would be. And remember, they're using the term amount. So we want to know how many moles would be possible to be produced. So essentially, you're just going back to good old mole ratio. So remember, we started off with 1 mole of each, right? So we have 2 reactants. Technically, we don't have a limiting reactant because they're the same value. But if you have a question where the mole value is different here, you would have to determine which one is your limiting reactant before you can determine your moles of product. But in this case, they're the same value, so you're just looking at the amount of product here. So it's a 1 to 2 ratio. So essentially, if we were to have all of this 100% being converted, we would have made 2 moles of product because we have 1 to 2 ratio. So remember to set up the mole ratio, you can use either one. I'll use hydrogen here. You're basically using the coefficients. So we have 2 moles of HI for every 1 mole of hydrogen. So it'd just be 1 times 2 divided by 1, which gives us 2 moles. Okay, so now the last part, this will lead us into the last part here. What is the percent reaction of the HI in the equilibrium mixture? So meaning what they want to know is essentially what is the percent yield. So we looked at this already in this chapter. So the percent yield or percent reaction is essentially the equilibrium yield over the theoretical yield, which is essentially your stoichiometry yield times 100. So this percent, and this is a good point to bring up, the percent yield or percent reaction can be done using either concentrations or mole values. So you can compare equilibrium moles to theoretical stoichiometry moles, or you can compare equilibrium concentration to stoichiometry concentration. Either way, you're going to end up with the same percentage value. So I'm going to use moles here since we have them handy. So our theoretical mole value for our product is the 2 moles we just solved for. And our equilibrium mole value, if we go back over here, the amount of moles of HI at equilibrium was 1.56 moles. So essentially we're doing 1.56 over 2 times 100%. So this is actually going to give us a value of 78%. So what does this mean? It means at equilibrium, we have 78% product, which means the remaining 22% is essentially your reactants, right? So this is a case, remember equilibrium is anywhere between 1 and 99%. So this is a case where we definitely have an equilibrium, and it's an equilibrium that tends to favor the products because we have more than 50% product here. Okay, so it's a very similar question to the first example we did, looking at solving for K, this one over here, where you had to take the square. The only difference is they're asking you kind of a different variety of questions. Especially I wanted to go over this percent reaction. Okay, so a lot of students get confused with that. Really just think of that as percent yield. So it's how much was made at equilibrium in comparison to how much would be made using just straight up stoichiometry. Okay, so the last piece to this is I want to show you something that will, I think, help you out a lot when you are solving for X with your K values. So this is something called a 100 rule, the 100 rule. Okay, let's backtrack. So let's say you had a K value of 400 and we had 3x squared over 20 minus 2x. Okay, so let's say you had a situation like this. So we're trying to solve for x, right? So we have our K expression set up, we have our equilibrium values that we're plugging in here, and we're trying to solve for x. Now, the examples we've looked at so far were a square over a square, right? So you were able to take the square root of both sides. But you're going to come across situations where it's not always going to be a square over a square. Right, so here I have a 2 over essentially just a 1, an x. So it's like x squared over x. So you're going to have to still factor out for x. That's really the goal of this because we need that in order to kind of continue on with our questions. But there's a way that we can try to prove if x is of significance or not. Okay, so what I mean by that, and it describes it up here as well. When you're subtracting x from a value, so let's say we have 20 minus 2x, you can come across a situation where x is very, 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 very small. So meaning, even though you're subtracting 2x from 20, you can have an x that's so small and insignificant that it basically rounds to 20. Okay, I'll give you an example. So let's say we had 20 minus 2x, and let's say we solved that x was equal to 0.000000001. Okay? Even if you were to multiply this by 2, 20 minus 0.0, how many zeros do they do? 1, 2, 3, 4, 5, 6, 7. Okay, so we have 0.1, 2, 3, 4, 5, 6, 7 with a 2. Guess what? You're going to get 19.00000, oh sorry, I should say 999999998. like, essentially, this is the same thing as saying, guess what? It's pretty darn close to still being 20. So there's a way that we can actually do a quick little calculation to see, does X have significance for this question or not? Okay, so essentially what you want to prove is, does your X value create a change in of at least 1/10? Okay, but what we want to see here is it significant in comparison to your initial concentration? So here's what you're going to do. You're going to take your initial concentration and you're going to divide it by KEQ. So you take the initial concentration and you divide it by your K. If the answer to this is larger than 100, even if it's 100 bang on or 101, even if it's 99, I would round that to 100, okay, but it has to be within 1. So if it's 92, you would not be able to say that it's 100, okay? 99, 98, yes. 95, I would still say no. Okay, but as long as if it's 100 or more, what that essentially means is you don't have to worry about subtracting X from your initial concentration, because it's so small that the difference is not really going to be felt when you actually go to calculate your values. And you'll notice here, right, 0.42 minus X would just become 0.42. Okay, so we're going to do an example where we're going to put this into effect, but that's pretty much what you're doing. So the value that you're putting here in your numerator is the item that you are trying to see, will it have an impact with the X? So typically it's the thing that you're trying to subtract X from. So in this case, it would be our 20. So like 20 divided by 400. Now, what happens if it's not above 100? What if you have that 97 or 95 or 2 or whatever it is, something under 100? That is when you are going to have to factor out using the full-blown quadratic equation. So meaning, even if you have an X squared and an X, that doesn't mean, oh, I can't solve for X in this case. Well, no, of course you can. You're using the quadratic equation. So when you're doing quadratics, if you're familiar with this from math, or if you remember anything about this, typically you end up with 2 X values. Right? You get 2 answers when you're doing this. So whenever you have to end up doing the quadratic equation, typically one will be deemed invalid and the other one is obviously valid. Okay, so what I mean by that is, first of all, let's say we had a situation where we were doing, let's do our 20 minus 2x again. Okay. 0.5. Okay, so let's say we plug in our values in our quadratic and we get 2x values. We have like -2 and 0.5. Okay, so first of all, you can never have an X value that is negative. Okay, so if you're doing this quadratic and one of the 2 values you get as your answers is a negative value, that is invalid. Okay, you cannot have a negative X. So in this case, this would be our situation. So you're probably wondering, well, what happens if you have 2 positive values? Okay, typically one will make sense and the other one won't. Okay, so I'll give you an example of this one. Okay, we'll still use our 0.5. So let's say we had 2 positive values. One is 21 and the other one is 0.5. Okay, well, look at where you're going to be plugging in your X value to. It has to give you a positive concentration. So for example, if the answer is 21, I'm going to have 20 minus 2 times 21. So I'm going to get a negative result here for my equilibrium concentration, which again does not make sense. So you'll either have a negative result with a positive. You always go with the positive, of course. If you have 2 positive results, look to see where you would be plugging X into. One will make sense and the other one won't. All right, so whenever you're doing quadratic, remember you're only doing this if the 100 rule does not work. And we're going to do an example of the 100 rule in our next piece here.